Improving sleep is often approached through bedtime habits. However, at the individual neuron level, initiating sleep means engineering a specific, targeted neurological state. Biologically, the mandatory gateway to rest is non-rapid eye movement, or NREM, stage 1. This stage marks the official transition from wakefulness to the early phases of sleep. Entering this state requires the brain to abandon high-frequency waking activity in favor of theta waves, which oscillate between 4 and 8 Hz. These waves must dominate a specific spatial coordinate, the brain's midline region. This area, tracked by the FC, CZ, and PZ electrodes, is where the transition to sleep is physically anchored. If theta dominance is not established over this midline, the biological transition is blocked. The subject remains consciously awake regardless of physical fatigue. Inducing sleep, therefore, requires targeting the midline with a frequency within the theta band, specifically at the 6 Hz center point. To generate these oscillations mechanically, researchers employ binaural beats. This illusion occurs when slightly different tones are presented to each ear independently. If a 250 Hz tone enters the left ear and 256 Hz enters the right, the brainstem identifies the 6 Hz difference. This forces surrounding brainwaves to synchronize with the beat. While EEG data confirms that binaural beats successfully entrain theta waves, they frequently fail to induce sleep. The cause of this failure is psychological. The synthetic nature of the sine waves is often perceived as an uncomfortable stimulus, triggering the amygdala. When the amygdala is activated, the resulting emotional aversion spikes levels of anger and tension. These states of arousal effectively override the mechanical entrainment of the theta waves. Mechanical entrainment is functionally ineffective if it simultaneously causes psychological stress. A successful intervention requires a secondary agent to mask the stimulus and maintain calm. To resolve this, researchers introduced Autonomous Sensory Meridian Response, or ASMR, triggers as an acoustic mask. While ASMR is often compared to music-induced chills, the physiological mechanisms of the two states are distinct. Music chills represent a high arousal state driven by the sympathetic nervous system, which is characterized by a significant increase in heart rate. ASMR triggers a state of parasympathetic activation. In this state, the heart rate decreases and skin conductance increases, indicating a physiological shift toward profound relaxation. Neural imaging reveals that ASMR reduces functional connectivity within the default mode network, or DMN. By lowering this connectivity, ASMR reduces processing in the frontal lobes, which quiets the internal, self-referential thoughts that often prevent sleep onset. The study utilized dynamic natural sounds, such as rain and waves, played at a clear intensity of 60 decibels. The objective was to bury the 6 Hz binaural beat underneath this 60 decibel ASMR mask, allowing the entrainment to occur without alerting the amygdala. This sensory delivery method allows this 6 Hz signal to reach the brainstem, while the psychological response remains one of calm rather than tension. In session 1, researchers tested different decibel ratios to identify the specific threshold where the binaural beat becomes effective without becoming an annoyance. They tested the binaural beat at 45, 30, and 20 decibels, all layered beneath the consistent 60 decibel ASMR mask. This EEG data tracks theta power across 7 brain regions for each ratio. In the midline region, the 45 and 30 decibel ratios both generated the required theta spike. However, prefrontal data on the left shows a severe negative drop for the 45 decibel beat. At 45 decibels, the synthetic sound was loud enough to be noticed by the listener, which actively disrupted relaxation in the frontal lobes. Conversely, the 30 decibel ratio, labeled here as CS2, maintained positive theta power in the prefrontal region, indicating that the beat was successfully masked. The results isolate the 30 to 60 decibel ratio as the specific threshold needed to induce midline sleep oscillations while preserving prefrontal calm. Session 2 compared this combined 30 to 60 decibel model against isolated single variables, a silent sham, the binaural beat alone, and the ASMR trigger alone. The binaural beat alone control confirmed successful theta entrainment, but subjects reported significant increases in anger and tension. The ASMR alone control increased calmness and generated frontal theta activity, but failed to produce the deep midline theta required for sleep. Only the combined stimulus captured both required metrics, the midline theta spike for sleep induction and the psychological state of calmness. Beyond theta waves, the combined stimulus was the only condition that significantly reduced the brain's beta power. Beta power is the physiological marker of high cognitive arousal and vigilance. Reducing it is a critical step in terminating the waking state. By balancing these two variables, the study satisfies the three core requirements for sleep: generating midline theta, establishing emotional calm, and suppressing beta activity. The historical failure of binaural beats highlights the limitation of relying solely on mechanical entrainment to alter human brain states. The brain does not process information purely as a machine. All sensory input is filtered through the amygdala to determine its emotional context. The 30 to 60 decibel acoustic mask is effective because it targets two distinct neural pathways, providing the required neurological entrainment while simultaneously modulating the psychological response. This coordination allows the physiological and emotional requirements to coalesce into a single outcome: NREM Stage 1 sleep. While pharmacological sedatives act systemically on the nervous system and often produce side effects, this method targets specific midline oscillations through a non-invasive auditory signal. The research demonstrates that psychological stability and brainwave entrainment are codependent, providing a new framework for how we develop future acoustic therapies.